Hello everybody and welcome to the video on rationalizing denominators of a radical expression. Let's just take a look at a couple of opening expressions here. I have 5 divided by the square root of 3, and I also want to take a look at 2 over the cube root of 7. So the idea behind rationalizing denominators, somehow, some way, somewhere, someone, I don't know who, what, when, where, why, said that it is improper to have radicals in the denominator. So I'm not quite sure why, but our game now is to get rid of radicals out of the denominators. So let's take a look at square roots first. The interesting thing regarding square roots is to take a look at the fact that if I take the square root of 3 and I multiply it by the square root of 3, let's just note that we can rewrite this as the square root of 3 squared. So now there's 2 ways to take a look at this. We can look at this the first way, so I'm just going to put a 1 right here. First way is to note that the square root and the squaring undo one another. So if these 2 operations undo one another, then let's just note that we end up with the number 3. And implied, let's just recall, is that the exponent here is 1. Another way, which we will take a look when we don't have square roots, is to also note that we could take the square root of 3, and we can rewrite this as 3 raised to the 1/2 power. So now the question then becomes, is recall that with like bases we add exponents. So if I take a base of 3, since I have a base here of 3 and a base here of 3, then what do I raise this one to, so that when I take the bases and use my rules of exponents, I get 1/2 plus whatever that special number is, and note that we want that to equal to 1. Well, clearly we know that 1/2 plus 1/2 is going to equal to 1. So notice that if I take 3 to the 1/2 and I take 3 to the 1/2, this is equal to 3 to the 1/2 plus 1/2, which is 3 to the 1, which is equal to 3. Moral of the story is, let's just note that we've removed the radical. Okay, we have removed the radical. So coming over here to cube roots, so with the cube root of 7, all right, so note, I think the easiest and most straightforward way of viewing this one is to note that we can rewrite this as 7 to the 1/3 power. So again, with our rules of exponents, I know I have to have a base of 7. So now the question is, what do I raise this 7 to, so that when I add these 2 together, that I get a base of 7, but I want my exponent to equal to 1. So hopefully what you'll see is that this question mark really becomes 7 to the 1/3, 7 to the 2/3, because when I add these together, I get 7 to the 1/3 plus 7 to the 2/3, 7 to the 1/3 plus 2/3, which is equal to 7 to the 1st power. All right. And notice that 7 to the 1st power, no matter how you slice and dice these, is just equal to 7. So notice here that we have removed the radical. So another way of viewing this is I can take the cube root of 7, and then I'll multiply that by the cube root of 7 squared. So it depends on how you're going to want to take a look at this. Okay, because this then becomes the cube root of 7 times the cube root of 49, etc. and so forth. Anyways, that's about as far as I'd like to go. So to rationalize the denominators means to remove the radical. So 5 over the square root of 3. So let's just note that to remove the square root, we just multiply by the square root of 3. So what I multiply on the bottom, I have to multiply on the top. So I get 5 square root of 3. And we know that the square root of 3 times the square root of 3 is 3. And notice that the denominator has been rationalized. So if I have 2 over the cubed root of 7, then we already know that we have to multiply, or in this case, I think it's easier to rewrite this as 7 to the 1/3 power. So note that we have to multiply 7 to the 2/3, 7 to the 2/3. So notice we get 2 times 7 to the 2/3 power divided by 7. Let me put a bracket right here. All right, so this becomes 2 times the cubed root of 7 squared, which is 2 times the cubed root of 49. And all of these are divided by 7. And there's nothing else to do to reduce. So that's our game. This is all we're going to do. So let me pull up a couple of examples here. Again, just continuing on with this concept. Kind of mix up some squares and square roots and cubed roots. So we have the cubed root of 3 divided by, the square root of 3 divided by the square root of 7. So again, to remove the square roots out of the denominator, I have to multiply the denominator by the square root of 7. So I have to multiply the top by the square root of 7. So note that the square root of 3 times the square root of 7, we already know is going to be the square root of 21. Divided by, and we know the square root of 7 times the square root of 7 is equal to 7. 21 does not reduce any further. So we've accomplished our goal. All right, so the idea, remove the radical from the denominator, simplify if necessary. So let's take a look at the square root of 14x divided by 5y squared. So let's just note that we can rewrite this as the square root of 14x divided by the square root of 5y squared. So we get the square root of 14x. And note that the y squared can come out as a y, and we get the square root of 5. So simplify first, all right? So we've cleaned up that, and now notice that to get the radical, remember we're just going to work with the radical. So here we have to multiply the denominator by the square root of 5, and here we get the square root of 5. So notice down here on the bottom, so we get a y, and root 5 times root 5 is just 5y. Okay? And then notice up top, up here, we're going to get the square root multiplying by 5. We get the square root of 70. And it looks like we get an x hanging out right here. Okay? So the square root of 70, there's nothing to do with this one. So basically we're done. The only thing we can do, I don't know, write that as a 5y instead. I don't know. Depends on how picky they want to be. All right, let's take a look at the cubed root now of 4 over 9x squared. Okay, so again, we'll rewrite this as the cubed root of 4, cubed root of 9x squared. All right. So again, if it helps, let's just take that denominator and we can rewrite this as 9x squared raised to the 1/3 power. So again, what do we raise 9x squared? So again, remember that was 2/3. So now we have to multiply the bottom by that. And up here, I'm just going to write the cubed root of 9x. And then we'll go ahead and square that because we got to clean that up. So notice that when I take the bases, 9x and 9x squared and 9x squared, that's going to be the base. I add the exponents, so let's just notice on the bottom, we just end up with this 9x squared. And up top, there's nothing to do here, so we get a cube root of 4. And here we get the cubed root of 81 x squared. Okay. And let's just observe that 81, all right, again, I've already pre-worked this, is 27 times 3. So again, the question is, how can I reduce 81? So I need to find something cubed. So now we get the cubed root of 4. And since 81 is the cubed root of 27 times 3, the 27 comes out of the cubed root as a 3. And inside we have the cubed root of 3x squared. So I get 3, and then this has to all be over 9x squared. So we got 3, so notice 4 times 3 is 12. So cubed root of 12x squared divided by 9x squared. And so our last step is that the 3 goes into the 9, so we just get this cubed root of 12x squared divided by 3x squared. And we have now completed our goal. All right. So the cubed roots, they present an interesting little challenge, but it's nothing that we cannot overcome. So last example regarding these is 6 divided by 4 x to the 4th y. Okay, so we can break this apart using our rules. So we get cubed root of 6 divided by cubed root of 4 x cubed y. And let's just note that, I'm sorry, this should be x to the 4th. So let's just note that this x to the 4th is x cubed times x, and this x cubed can come out of the cubed root, so I get x cubed root of 4xy. So again, rewriting in its exponent form, I get the cubed root of 6, so I get x and then 4xy to the 1/3. So let's just note now we have to multiply 4xy to the 2/3, and here we get the cubed root of 4xy squared. Okay, just keeping it in its radical form. Okay, so up here at the top we get the cubed root, so I put that inside, so we get the cubed root of 6 times 4 is 24. I'm sorry, this here we gotta clean this up. So it's going to be 6 times, and note that this thing is squared, so we get 16 x squared y squared divided by, and let's just note that when we add these two we get a 1, so on the bottom we get a 4xy, so x 4xy. So up top, 16 times 6 is the cubed root of 96 x squared y squared divided by 4 x squared y. Now again, I did do some pre-work here, and let's just note that 96 is 8 times 12 x squared y squared divided by 4 x squared y, and that 8 can come out as a 2, so we get 2 cubed root of 12 x squared y squared divided by 4 x squared y. So our final answer is the cubed root of 12 x squared y squared divided by 2 x squared y. Okay, so it is a little bit of a chore on some of these to do some rationalizing here, but again, this is basically the foundation of rationalizing the denominators. Okay, so we got one more that we need to take a look at, and that is square roots that are something perhaps maybe in the form of, say that we want to simplify. Let me just pull this example up. Say -2 divided by the square root of x plus 3. Okay, so now we got to introduce a new term here, And this new term is something, especially for those of you that are going on, okay, to trigonometry, to calculus, and you're also going to see this again in the college algebra as well. And it's this little term called conjugate binomials. And let's note we're already familiar with binomials. That's just the sum of two terms. So for example, if we have a plus b, then the interesting thing is that it's conjugate binomial, if you will, conjugate just meaning the opposite but similar. So the opposite of a plus b would be a minus b. So opposite but similar. So they're similar in that they have the a's in this arithmetic. So this is the difference part right here. So if you have a plus b or a minus b, its conjugate is a plus b. And we have seen these already because we talked about how to factor a squared minus b squared, and note that this factors to a plus b, a minus b. So it is interesting to note that if I have the square root of a plus b, and I multiply by its conjugate, which is the square root of a minus b, let's just note if we FOIL this, I get the square root of a times the square root of a minus the square root of a times b plus, and now if I multiply these guys, I get the square root of a b, and then when I multiply here, I get minus b squared. So notice here, I get a, these guys drop out, minus b squared. So notice that if I multiply conjugate binomials, then I'm just going to get this first thing squared minus the second one squared. And notice I can just go a minus b squared. Okay, little shortcut here. So if I have the square root of a minus the square root of b, and I multiply by its conjugate, the square root of a plus b, then again note that I'm saying that all you have to do when you multiply conjugate binomials is just take this first term and square it minus the second term. Oh, I need a square root there. Minus the second term here. I don't even need this first bracket here. And notice that I get that this is a minus b. So notice that when I multiply conjugate binomials, we have the fact that the radicals go away. So notice now if I want to come back to our first example, so I got this minus 2 divided by the square root of x plus 3. Then note if I multiply by its conjugate, I get the square root of x minus 3, square root of x minus 3. Then notice that I get minus 2 times the square root of x, and then minus 2 times minus 3 becomes plus 6, divided by, now again, since I'm multiplying these conjugate binomials, you don't really have to FOIL it out. I mean, feel free if you want to, but I get the square root of x squared minus 3 squared. So here I get minus 2 square root of x plus 6 divided by, and the square root of x squared is just x minus 9. And there's nothing to factor and cancel, so we already have this in its simplified form. So our next example, let's take a look at the square root of a divided by the square root of a minus the square root of b. So again, to get the square roots out of the denominator, let's multiply by the conjugate. So this is the square root of a plus the square root of b. So we get the square root of a plus the square root of b, because that's just the number 1 in its grand total. So the square root of a times the square root of a. And note we get the square root of a times the square root of b, which is the square root of AB. And then again, we get the square root of A squared minus the square root of B squared. So here we get A plus the square root of AB divided by A minus B. And there's nothing to factor, and there is nothing to simplify. Okay, let's take a look at the very, very last example of this video. So we get 3 root 2 plus square root of 6 divided by 4 root 2 minus the square root of 6. Okay, so again, to rationalize the denominator, I'll go ahead and multiply by the conjugate. So 4 root 2 plus root 6 and 4 root 2 plus root 6. Okay, so let's just do the denominator first. I think that's going to be the simple part. So let's just notice that we get 4 square root of 2 squared minus the square root of 6 squared. Okay, so we'll just get that done and out of the way. So notice up top we have to FOIL. So 3 root 2 times 4 root 2, so 3 times 4 is 12. Square root of 2 times the square root of 2 is just going to be 2. Square root of, so 3 root 2 times root 6, so I get plus 3. Root 2 times root 6 is root 12. Okay, square root of 6 times 4 root 2, so here I get 4. And then 6 times 2 is 12. And then root 6 times root 6 is just going to be 6. Right, so here we get 24. And then notice that 12 is 4 times 3. So the 4 comes out as a 2. 3 times 2 is 6. And we still have a root 3 on the inside. Again, this 12 is 4 times 3. 4 comes out as a 2, so I get plus 8. Square root of 3 plus 6. Divided by 16 times 2 minus 6. Again, I'm just going to take it a step at a time. So 24 plus 6 is 30. And 6 root 3 and 8 root 3 is a grand total of 14 root 3's. Divided by 16 times 2 is 32 minus 6, so we get a 26. Okay, so notice there's a 2 up top. We can pull the 2 out. So I get 15 plus 7 root 3 divided by 2 times, let's see, what is this? 26, what is that, 13? So the 2's drop out. So we end up with 15 plus 7 root 3 divided by 13. And notice our mission is complete. It's not that we have a single number, it's just that the denominator has been rationalized. That is, there's no more radicals in the denominator. So, all right, that completes this video on rationalizing denominators. Hope this helps you out, makes sense. If you have any muddy points or questions on the video, please feel free to share those with me in our warm-up. So outside of that, I will see you in the class.